in electrical circuits, particularly 3-wire and 4-wire configurations, determining whether the neutral conductor should be counted as a current-carrying conductor when adjusting ampacity is crucial for safe and compliant installations. The necessity of counting the neutral conductor hinges on several factors related to the circuit's characteristics and the types of loads it serves. Understanding these factors ensures that conductors are appropriately sized to prevent overheating and potential hazards. Generally, the neutral conductor in a 3-wire or 4-wire circuit is counted as a current-carrying conductor under specific conditions outlined in the National Electrical Code, specifically Article 310.15. The primary reason for this classification stems from the potential for the neutral conductor to carry significant current, particularly in circuits serving nonlinear loads. Nonlinear loads, such as those found in modern electronic devices, including computers, LED lighting, and variable frequency drives, produce harmonic currents. These harmonic currents, especially the third harmonic and its multiples, can accumulate in the neutral conductor of a 3-wire or 4-wire circuit, leading to a substantial increase in neutral current. When harmonic currents are present, the neutral conductor may carry a current equal to or even greater than the phase conductors. Therefore, it must be counted as a current-carrying conductor for ampacity adjustment purposes. Firstly, consider a 3-wire circuit consisting of 2 phase conductors and a neutral conductor. If this circuit primarily serves incandescent lighting or other linear loads, the neutral conductor is generally not required to be counted as a current-carrying conductor. This is because, in a balanced linear load scenario, the neutral current is minimal or non-existent. The current returning through the neutral conductor is essentially the difference between the currents in the 2 phase conductors. Under perfectly balanced conditions, these currents cancel each other out in the neutral conductor. Secondly, examine a 4-wire circuit which typically includes 3 phase conductors and a neutral conductor. If this circuit serves a balanced set of linear loads, the neutral conductor may not need to be counted as a current-carrying conductor. Again, the principle of current cancellation applies, assuming the loads are evenly distributed across the 3 phases. However, if nonlinear loads are present, the neutral conductor must be counted due to the potential for harmonic current accumulation. Thirdly, when dealing with multi-wire branch circuits, which share a common neutral conductor, it is essential to consider the type of loads connected to each phase. If the multi-wire branch circuit serves primarily nonlinear loads, the neutral conductor must be counted as a current-carrying conductor. This is because the third harmonic currents from each phase add together in the neutral conductor, rather than cancelling out. This additive effect can result in a neutral current that significantly exceeds the current in any of the individual phase conductors. The National Electrical Code, or NEC, provides guidelines for adjusting the ampacity of conductors based on the number of current-carrying conductors in a raceway or cable. When the number of current-carrying conductors exceeds 3, adjustment factors must be applied to reduce the allowable ampacity of the conductors. This reduction is necessary to account for the increased heat generated by multiple conductors in close proximity. If the neutral conductor is counted as a current-carrying conductor, it must be included in this count, which may result in a more significant reduction in the allowable ampacity of the phase conductors. One should consult NEC Table 310.15 Current for the applicable adjustment factors based on the number of current-carrying conductors. This table provides a percentage reduction in ampacity for various numbers of conductors, ensuring that the conductors are not overloaded and that the temperature rating of the conductors and associated equipment is not exceeded. Furthermore, consider the specific application and the likelihood of future changes in the type of loads connected to the circuit. If there is a possibility that nonlinear loads may be added in the future, it is prudent to count the neutral conductor as a current-carrying conductor from the outset. This proactive approach ensures that the wiring is adequate for any potential changes in load characteristics and avoids the need for costly and disruptive rewiring in the future. To illustrate these concepts with examples, consider 3-wire circuit supplying power to a commercial office space. If the office space primarily uses computers and LED lighting, which are nonlinear loads, the neutral conductor must be counted as a current-carrying conductor. In this scenario, the third harmonic currents generated by the electronic equipment will accumulate in the neutral conductor, potentially causing it to overheat if it is not properly sized. Therefore, the ampacity of all conductors, including the neutral, must be adjusted based on the number of current carrying conductors. On the other hand, if the same 3-wire circuit supplies power to a workshop that primarily uses power tools with traditional induction motors, the neutral conductor may not need to be counted as a current carrying conductor. Induction motors are generally considered linear loads, and the harmonic currents they generate are typically minimal. In this case, the neutral current will be relatively low, and the ampacity of the conductors may not need to be adjusted. However, it is essential to verify the specific characteristics of the loads and consult with a qualified electrical engineer to ensure compliance with the NEC and other applicable standards. Similarly, consider a 4-wire circuit in a data center. Data centers are known for their high concentration of nonlinear loads, including servers, network equipment, and uninterruptible power supplies, or UPS. These devices generate significant harmonic currents, which can cause substantial neutral current. In this scenario, the neutral conductor must be counted as a current carrying conductor, and the ampacity of all conductors must be carefully calculated to ensure that the wiring can handle the expected load. The use of oversized neutral conductors or the implementation of harmonic filtering techniques may be necessary to mitigate the effects of harmonic currents and prevent overheating. In residential applications, the decision of whether to count the neutral conductor as a current carrying conductor may depend on the specific appliances and equipment used in the home. For example, if the home has a large number of LED lighting fixtures, computers, and electronic devices, it may be prudent to count the neutral conductor as a current carrying conductor. This is particularly true in homes with multi-wire branch circuits, where the additive effect of harmonic currents can be more pronounced. However, if the home primarily uses incandescent lighting and traditional appliances, the neutral conductor may not need to be counted as a current carrying conductor. In summary, determining whether to count the neutral conductor as a current carrying conductor when adjusting ampacity requires a careful evaluation of the circuit's characteristics, the types of loads it serves, and the applicable requirements of the NEC. It is important to consider the potential for harmonic current generation and the additive effects of harmonic currents in multi-wire branch circuits. Consulting with a qualified electrical engineer and following the guidelines in the NEC will ensure that electrical installations are safe, compliant, and capable of handling the expected loads. Remember to use appropriate adjustment factors from NEC Table 310.15 when the number of current carrying conductors exceeds 3. These adjustment factors reduce the allowable ampacity of the conductors to account for the increased heat generated by multiple conductors in close proximity. In addition to considering the number of current carrying conductors, it is also important to consider the ambient temperature and the presence of other heat sources in the vicinity of the conductors. High ambient temperatures can further reduce the allowable ampacity of the conductors, and additional adjustment factors may be necessary to account for these conditions. Also, ensure that the conductors are properly installed and that the connections are tight and secure. These connections can generate heat and increase the risk of overheating and fire. Regularly inspect electrical wiring and equipment to identify and correct any potential problems before they become serious hazards. When in doubt, always err on the side of caution and consult with a qualified electrical engineer. They can provide expert guidance and ensure that electrical installations are safe, compliant, and reliable. The NEC is updated regularly to reflect changes in technology and best practices, so it is important to stay informed about the latest requirements and recommendations. Continuously educating oneself about electrical safety and wiring practices is essential for anyone working with electrical systems. Understanding these principles is crucial for ensuring safety and compliance in electrical installations. The neutral conductor, in certain configurations, plays a vital role in carrying current, necessitating its inclusion in ampacity adjustments to prevent overheating and ensure safe operation. The presence of nonlinear loads, multi-wire branch circuits, and potential future modifications should all be considered when determining whether to count the neutral conductor as a current carrying conductor. Always consult the latest edition of the NEC and seek guidance from qualified professionals for specific applications and interpretations. By considering these factors and following the guidelines in the NEC, one can ensure that electrical installations are safe, reliable, and compliant with applicable standards. This approach will help to prevent electrical hazards and protect people and property from the risks associated with overloaded or improperly sized conductors. Remember that electrical safety is paramount, and it is always better to err on the side of caution when dealing with electrical systems. Proper planning, installation, and maintenance are essential for ensuring the safe and reliable operation of electrical equipment and wiring.